everyone. Thank you very much for joining us today for a webinar on why magnetic measurements are so critical in power supply design. We're hosting this webinar today because many engineers are challenged with accurately measuring in-circuit magnetic devices, which impact proper inductor and transformer selection and reliable in-circuit magnetic power measurement. Before we get started, I'd just like to let everyone know that this webinar will be recorded and you'll be receiving an email afterwards with the recording, so you can go ahead and share it with anyone you think would be interested or rewatch it if you'd like. If you're interested in any of the other webinars that we'll be hosting or to download any of the free resources we have available, such as white papers or application notes, please go ahead and visit testforce.com/academy and you'll find everything you need right there. If during the webinar you have any questions, make sure you ask them in the Q&A section in the right side menu bar, and we will be sure to get to all of those questions as we get to the end of the presentation. I'd like to introduce Wilson Lee, Technical Marketing Manager at Tektronix. Wilson focuses heavily on design and design engineer engagement with the RF wireless, industrial power, and industrial automation markets. And now, without further ado, I'm going to hand it over to Wilson.
Thank you for attending today's webinar on practical magnetic measurements in switch mode power supplies. In switch mode power supplies, magnetic components, namely inductors and transformers, play important roles. Inductors serve as energy storage devices or filters. Transformers are used to convert voltage levels and to provide isolation. Transformers also play an important role in sustaining the switching or oscillation in switch mode power supply systems. Much of the switch mode power supply design processes rely on component selections as well as simulation models. However, due to parasitics, temperature, and other environmental effects, a power supply may not perform exactly as predicted by the datasheet or by the simulations. Thus, in-circuit measurements of inductors and transformers made under actual operating conditions can provide critical performance information. So the webinar today will cover measurement challenges on selecting and qualifying those right magnetic components, reliably measuring magnetized current and power loss, and determining overall system impact. We hope that attendees today will come away with better understanding of how to properly select and qualify their in-circuit magnetic components and reliably measure their magnetic devices in their switch mode power supplies. It is expected that the magnetic components such as inductors, coupled inductors, and transformers operate in stable condition such that the power supply is not driven to an unstable condition. The stability is based on the function of these magnetic devices such as storing energy, filtering, switching, and isolation. Now ultimately, switch mode power supplies can be made smaller and more efficient by operating at higher switching frequencies. Now this reduces margin for error for design variations and operating tolerances, particularly around the switching frequencies. And the switching frequency and its stability depends highly on the magnetic components in the switching elements around the switch mode power supply. Proper measurement and understanding of your in-circuit magnetics plays the following roles in your overall system design considerations. Such measurements, such as power loss, due to the inductor transformers, which if not handled correctly result in heat. Reducing losses help reduce heat generated and also have good heat dissipation mechanisms. These issues cascade to other system consideration issues, particularly operating over temperature specs. Higher thermals will impact performance across your entire circuit, as well as lead to impact of noise onto your circuit itself. Ultimately, at a device level, you will start to see either shortening of the lifespan of your magnetic device, such as coil failure or shorter life, as well as overall impact to your circuit as a whole. The switching frequencies and waveforms are complex, particularly as we work in higher frequency ranges in which are including the multiple frequencies that are within. There are a lot of variations in your in-circuit magnetic measurements that will be impacted by the changes such as your power on, steady state, changes in source, as well as changes in temperature and the introduction of unforeseen transients such as ringing noise. Let's talk about the inductance definition, which is the property of an electric conductor or circuit that causes electromotive force to be generated by a change in the current flowing. Now, the unit of measurement for inductance is henries. As we talk about inductors later in the webinar, inductance exhibits increasing impedance with frequency and impeding higher frequencies more than lower frequencies. But in short, inductance may be determined as a function of voltage and current over time. Now, this is a perfect job for an oscilloscope which is equipped with a voltage probe, current probe, and is able to perform integrated plots of X versus Z on current and voltage. As we'll cover in the webinar, the inductance of devices can be measured automatically with an oscilloscope equipped with such power analysis software. One point on magnetic cores. Magnetic cores effectively are magnetic materials with high magnetic permeability used to confine and or guide the magnetic fields in electrical, electromechanical, and or magnetic devices. As we talk about an inductor, which is also called a coil, a choke, or a reactor, an inductor is effectively a passive two-terminal electrical component that stores energy in a magnetic field when an electric current flows through it. It is also worth mentioning for our webinar that an inductor can also have multiple inductors on a single core. Now, it is worth also mentioning that in contrast to theoretical inductors in textbooks, the inductance value of a real inductor is dependent on multiple of things, particularly current levels, temperature, and the frequency of operation. In a power supply, these characteristics vary in real time with operating conditions. So as the figures you see in the upper right shows the basic inductor, which is a coil wound on a closed ferromagnetic core. And current of I, amperes, flow through the coil, which has N number of turns. So the inductance of the coil describes the relationship between the current flowing in the coil and then the magnetic flux. In building a better inductor, let's look at the reference equation in the lower right hand of the screenshot above. Inductance is a function of permeability mu. It's proportionate to the number of turns squared and then the size of the core. So generally speaking, we would like higher permeability materials as a function of getting a smaller size inductor. Now, as we talk about transformer definitions, and for levity's sake, we are not talking about Optimus Prime, the transformer. Actually, the transformer, as it relates to in-circuit transformer, is a device used to transfer electrical energy from one circuit to another. With alternating current, the transformer will either raise or lower the voltage as it makes that transfer. As such, transformers perform important functions in switch-mode power supplies. The first is isolation, in order to meet safety standards between input and output sides. The other important functional purpose is to step down or step up voltage so that the converters can operate in normal duty cycle ranges. It is worth mentioning that it is possible to obtain multiple outputs through multiple second windings, which you see in the upper right-hand portion of this PowerPoint slide. Now, some of the common converters which use isolation transformers will range from flyback to forward, full bridge, push converters, as well as full bridge boost converters and isolated converters. Let's talk about the definition of a BH curve. It is effectively something that will visualize the performance of an inductor and its cores. Now, designers use the BH curve or hysteresis curve like the one shown in the above figure. And then within the equation, H is the magnetized force in the device. It is measured in amperes by meters and is proportionate to the current. Now the resultant flux density, B, is proportionate to the integral of voltage. So as you can see, the slope of the BH curve is effectively the permeability of the magnetic material as measured in μs. Now the permeability, again, is the rate at which the magnetized force H, driven by current, produces the flux density B as measured in integrated voltage. Manufacturers supply BH curves for their core materials as part of their specifications. And a magnetic component is designed based on operating voltage, current, topology, and the type of power converter. Generally speaking, the goal is to avoid saturation and operate within the linear region of the BH curve. Now, as you look at the chart and the curve on the right-hand side of this slide, some things to highlight. Again, the BH curve, or the hysteresis characteristics, you'll notice that the width of the curve indicates loss or power inefficiency in the power supply. So that the wider the BH curve, the less efficient the device is, in that you'll need more current to remove flux density. Other considerations is the saturation flux density. This is the point at which additional magnetized force no longer produces flux density. And as you can see with the figure in the above equation, saturation is reached at the point where the slope flattens out. So again, no matter how much more magnetized force you insert into the device, you will not produce any more flux. We want to begin to talk about inductance measurements and wanted to point out some currently used methodologies in getting such measurements. The first actually using an LCR meter. This approach is used by having the LCR meter and applying a fixed frequency and then observing the phase shifts between voltage and current as you see in the diagram on the right. Now this is useful, but it is useful at a single and typically lower frequency point, and typically at lower voltages. So regretfully, it does not really help us in actual operating measurements in circuit conditions. So what we're typically seeing are power supply designers often using simulation techniques to determine the appropriate inductor value for a design. After manufacturing the inductor, they verify the inductance using an LCR meter. While this is a good technique for confirming that the component is roughly the correct value, it is a poor predictor of in-circuit performance. Tektronix has come up with a way of measuring inductance using BH curves. Currently, there are no digital storage oscilloscopes in the marketplace that have this capability of analysis. Measurements are made by probing the voltage across the device, usually with a differential probe, and using a current probe to measure the current through the magnetic component. To determine the inductance, the application integrates the voltage over time and divides by the change in current. It also removes any DC offset and uses averaging to calculate the inductance value. The inductance measurement you can see in the screenshot above in the upper right hand side, and where you see channel 1 is the voltage across the inductor, and then channel 2 is the current through the same inductor. The current versus integral V plot gives us additional insight on the inductance value over multiple cycles. It shows how much DC offset is being retained in the inductor as it switches on and off. And as you can see, the I versus integral V measurements shown in the screenshot above, and where the yellow waveform in channel 1 is the voltage across the inductor, and the blue waveform in channel 2 is the current through the inductor. An oscilloscope, such as our 5 series MSO scope, can be used to perform an in-circuit measurement of voltage across and current through the winding of an inductor. Key items of information that we'll need are the number of turns N, magnetic length, and the cross-section area of the device itself. To ensure the stability of the power supply, it is important to characterize the operating region of a magnetic component while it operates in the switch mode power supply. So the software will plot the pH curve. We will look at the hysteresis. We'll also view whether or not we have reached saturation. Other key parameters which we do want to look at are the peak flux density, or BSAT, permeability, mu, remnant flux density, BR, which is the magnetic flux density that remains in the material after the magnetizing force, H, drops to 0. And then lastly, coercivity, which is HC, and the value of H required to drive the flux density, B, back to 0. Our automated software gives hysteresis plots of the magnetic component into the design to check if the magnetic components are at saturation or not. And if it is reaching saturation, this is an area of concern, as this would lead to instability in the power supply design. For in-circuit BH measurements on transformers, similarly we'll need a number of turns, current, as well as the area of the device in question. And what we're trying to point out here is that the software measurement on the BH plots will actually help isolate the magnetized inductor as highlighted in the block diagram above. Our power analysis software is capable of calculating the magnetic loss in a single winding inductor, a multiple winding inductor, or even a transformer. In the case of a single winding transformer, a differential probe is connected to measure the voltage across the primary winding. A current probe measures the current through the transformer, and the power measurement software can then automatically calculate the magnetic power loss. The magnetic power loss results are presented as shown in the figure above on the right, and it shows the total power loss in the magnetic component. Designers can then find the core loss from the component manufacturer's datasheet and derive the copper loss by subtracting the core loss from the total magnetic loss. With the MSO5 series and related advanced power analysis software that is using magnetics analysis capabilities, one can measure the magnetic loss, inductance loss, as well as magnetic property measurements very easily. What one needs to know is the operating frequency, physical characteristics, and desired voltage and current for each winding in order to measure the BH curve. The application does the rest through its complex algorithm. The required parameters for inductor design in switch mode power supplies can be designed and measured in with the software. Now, inductor and transformers are used as energy storage devices and are critical in switch mode power supplies, as well as linear power supplies. And some power supplies are also using inductors as filters in their outputs. But in the end, given the importance in power converters and the growing trends of magnetics and such things as wireless charging, it is essential to characterize these magnetic components properly to determine the power supply stability and overall efficiency. So magnetic analysis in our software, again, automates the following groups of measurements, that being inductance, magnetic loss, and the range of measurements within of the BH or hysteresis parameters. We hope that all of this will certainly enable you to have more confidence in your magnetic device selection as well as your switch mode power supply designs. Before we close today's webinar, I'd like to cover a few overall power-centric test solutions provided by Tektronix. Throughout the webinar, we've been leveraging measurements on our MSO5 series oscilloscope. The MSO5 series provides many firsts in the industry benefits. Firstly, it provides the user the choice of 4, 6, or 8 analog channels, while also providing technology called flex channel that enables the designer to choose between 1 analog channel or 8 digital. So in effect, you can have either an 8 analog channel scope or a 64 digital scope. The models range from 350 megahertz to 2 gigahertz in bandwidth. And it is a full 12-bit A to C resolution scope with very fast sampling rates of up to 6.25 gigasamples a second across each channel, as well as up to 125 million points of record length. More than enough to be your bench scope of choice for your power designs. And within of that, beyond of the magnetic measurements that we covered today, the 5 Series MSO also provides analysis software to more holistically enable you to look at power quality measurements such as ripple, slew rate, switching loss, SOA or safe operating area, modulation, harmonics, and overall power quality, while also providing very easy to use point-and-click report generations. I also wanted to go one step further and talk about power efficiency measurement on an MSO 5 Series scope. Efficiency is part of overall designs of what we talked about in-circuit magnetics and overall power efficiency. Effectively, we want to measure how much power at the input actually appears output. And so effectively trying to reduce the amount of waste or inefficiency, as well as conserving energy. So effectively, power supply efficiency here is very important, particularly around of the smaller form factors of power supplies, which the market is driving for. And here, as exemplified in this screenshot, is the ability to test multiple outputs with a one-time and go faster to market analysis solution. Power efficiency measurements is ideal for the 8 channels on our 5 Series MSO scope. And as you can see, where you want and need multiple output measurements. I wanted to touch base on Tektronix focus and expertise in high-performance probe solutions, particularly for those in the audience that are working on higher frequency, higher power switch mode power supplies that are now more commonly using silicon carbide or gallium nitride semiconductors. Tektronix has a one-of-a-kind solution, which is a galvanically isolated differential probe that provides absolute clarity of high differential voltage measurements in the face of very high common mode voltage. As shown in the upper right-hand part of this slide, we see the ideal state of a high-power switch mode power supply, where we see the region of CGS charge time to the Miller plateau, and then in the full state of conduction. But in reality, what we see are the screenshot on the left, which is the very strong, large common mode voltage overshadowing the differential voltage measurement which we want to make. And on the right is actually the absolute clarity which our galvanically isolated differential probe called IsoView enables the designer. There's something to consider through this presentation if you do need such a probing solution for your designs. Lastly, within of today's webinar, we also spoke of potential consequences of EMI and EMC noise transmissions. Tektronix has recently introduced additional software capabilities, namely EMC View, within of its overall real-time spectrum analysis portfolio. This EMC View is effectively EMI EMC test in a box, where you can quickly and efficiently gain insights across all global standards of EMC test standards in a very cost-effective way that will better enable you to get quicker and more accurate insights to pass EMC EMI tests.
Thank you for listening to our webinar on why magnetic measurements are so critical in power supply design. There was a lot of information there from Wilson, and we're just waiting for some questions to come into the Q&A box. If you have a question, feel free to type it into the Q&A section on the right-hand side of your dashboard, and we'll get to answering those. Also, I am going to post a quick poll up on the dashboard. It will be available for about 5 minutes, so while we're waiting for some more questions, feel free to fill in your responses. Okay. For those of you who attended, we'll be sending out a copy of the recording so that you can watch it again or share it with your colleagues. If you do have any questions that come up at a later point in time, don't hesitate to reach out to us at Testforce. You can reply to my email, or you can contact me easily by emailing support@testforce.com. Thank you very much, everyone, for your attention and participation today. I hope that you all have a great day, and we look forward to hearing your feedback.